Hello, and welcome to my new video series about calculus topics ranging from derivatives, integrals, first and second derivative tests, optimization, and more. Today's video is a prerequisite video about critical points that will prepare you for more advanced calculus topics. This video is the first in a three-part series about critical points, the first derivative test, and optimization. It's important to understand what critical points are, know how to identify them from a graph, and know how to solve for them using the first derivative. This will prepare you to use the first derivative test, which will allow you to solve optimization word problems. Before we jump into critical points, let's quickly review the concept of taking the first derivative of a function. Here we have a function that has algebraic terms such as 5x to the fourth, as well as transcendental terms such as e to the x. The first derivative of this function is either a, b, or c. Now go ahead and try this one on your own. Alright, we're back, and hopefully now you've attempted to solve this problem on your own. If your attempt was successful, you should have gotten that the first derivative of this function is in fact b. Alright, we're going to start off by rewriting our function. We'll keep the first two terms the same, but we want to rewrite 17 as 17 times x to the 0. This will help us see that the constant rule, which tells us that the derivative of any constant is 0, is really just another form of the power rule. Here we're using the power rule for the first term and the product rule for the second term. Finally, we know that the derivative of 17 is 0 by the constant rule, and we're also showing how it is a form of the power rule by bringing down that 0. This is your reminder to take the derivative of your constants. By not doing so, you will obtain the wrong solution from answer A, and when carrying out the power rule, always bring down your exponents as coefficients. If you don't, you'll get the wrong answer from answer C. We define critical points as points on a function's domain where the slope of the tangent line at these points is either 0 or undefined. It's important to recall that the slope of the tangent line at a point is another way of saying the derivative at that point. So we are essentially looking for points on a graph where the derivative is 0 or undefined. You should also note that these are called critical points because they mark a critical shift or change in the behavior of a function. Let's take a look at our first graph here. Here we can see at x equals a and at x equals b, we can draw horizontal tangent lines. We know that the slope of a horizontal tangent line is 0, and this tells us that our derivative at these points is 0, so these are critical points. We can also verify this using angles, because at either of these points, the tangent line makes an angle of 0 degrees with the horizontal x-axis, and when we take tangent of 0 degrees, it gives us 0, which confirms that the slope of the tangent line at these points is 0. Now that we've identified our critical points on this graph, we can write them in the form of ordered pairs. This means that at x equals a, we have the point a comma h of a, and at x equals b, we have the point b comma h of b. So on this graph, we found critical points at x equals a and at x equals b because the derivative or the slope of the tangent line at these points is 0. And we call h of a and h of b the critical values of these critical points. Now let's take a look at this second graph. Here we have a corner point. And if we look at the left and right of this corner point, we could see that we have unequal limits of our difference quotient. Now, the limit of the difference quotient is just another way of saying the derivative. Since we have unequal limits of the difference quotient on the left and right, then the limit does not exist. And this tells us that our derivative does not exist at this point, so we can conclude that our derivative is undefined at this point, and that makes it a critical point. Let's take a look at our last graph here On this graph, we have a point, and at this point, we have a vertical tangent line. We know that the slope of a vertical tangent line is undefined, and we can confirm this using angles. At this point, the tangent line makes an angle of pi over 2 with the horizontal x-axis, and we know that when we take tangent of pi over 2, it is undefined. This just confirms that the slope of a vertical tangent line is undefined, so our derivative at this point is undefined, which makes it a critical point. By looking at all of the graphs, you can see that each critical point marks a critical shift in the behavior of each function. Now, let's finally learn how to find critical points using the first derivative. Our first step is to take the first derivative of a function. Then, we set the derivative equal to 0 and we solve for x. Remember that the derivative of a point is the same as the slope of the tangent line at that point. So when we set it equal to 0, we're essentially looking for all the points on the function where the slope of the tangent line at those points is 0. Let's look at an example to make this a little more clear. In this example, we have a transcendental function f of x equals 2 cosine x plus sine squared x, and we are looking for the critical points on the domain 0 to 2 pi. The first step is to take the first derivative of this function. We can do this by using the rules for derivatives of trig functions, as well as the chain rule for that second term. If we do this, we get the first derivative to be negative 2 sine x plus 2 sine x cosine x. We can factor out the negative 2 sine x to get negative 2 sine x times the quantity of 1 minus cosine x. If we set this equal to 0, we get two parts. Negative 2 sine x equals 0, and 1 minus cosine x equals 0. This gives us sine x equals 0 and cosine x equals 1. For sine x equals 0, we get x equals 0, pi, 2 pi, and so on. For cosine x equals 1, we get 0, 2 pi, and so on. Now, these points would be our critical points, and since we are looking for them on the domain from 0 to 2 pi, we would only include 0, pi, and 2 pi. And if we look at the graph for this function, we can see that at 0, pi, and 2 pi, the slopes of the tangent lines at these points are all 0, which confirms that they are critical points. Now that we've done an example together, it's time for you to try the next one on your own. Find the critical points of the algebraic function f of x equals 2x cubed plus 6x squared. The critical points are given by either A or B. Take some time to pause this video and try this one on your own before the solution is revealed. Good luck! Okay, we're back. Hopefully now you've attempted to find the critical points of this algebraic function, and if your attempt was correct, you should have gotten that the critical points are negative 2 and 0, so let's dive into that correct solution on the next slide. We have our function here, f of x equals 2x cubed plus 6x squared. Now the first step to finding the critical points is to take the first derivative. Here our first derivative is 6x squared plus 12x, and we simply used the power rule on both terms. Next we can factor out a 6x, which would give us 6x times the quantity of x plus 2. Now if we set both of these parts equal to 0, we get 6x equals 0 and x plus 2 equals 0. Finally, when we solve for x, we have x equals 0 and x equals negative 2, which gives us our critical points. And it's important to remember in step 2 that you set the derivative equal to 0, but not the original function equal to 0, like the student did for answer A on the previous slide, which is how they got the incorrect solution, negative 3 and 0. Looking at the graph here, we could see at x equals negative 2 and at x equals 0, the slope of the tangent lines at both of these points is in fact 0, which confirms that they are critical points. Finally, let's have a little recap of everything we learned in this video. We defined critical points as points where the slope of the tangent line at these points is either 0 or undefined, as shown in these three graphs. We also learned how to find the critical points of a function by taking the first derivative, setting it equal to 0, in solving for x. Now before you go, here's a little challenge question. How can you use critical points to find where the maximum or minimum of a function occur? Stay tuned for the next video in the series to find out, and thanks for watching.